Hello, in this video I'm going to review the quiz number 2 from chapter 7 of Shigley's 10th edition. The question says, the shaft shown in the figure is driven by a gear at the left end milled key seat, drives a fan at the right keyway, and is supported by two deep groove ball bearings. The shaft is made from AISI 1020 cold drawn steel. At a steady state speed, the gear transmits a radial load of 6 kilopounds force and tangential load of 8 kilopounds at a pitch diameter of 2.5 inches. Draw a free body diagram, find the reaction forces, torsion, bending, moment, find the diameter d based on Gerber criterion, consider the shaft as uniform, and find the deflection equation, and finally check for the yielding. So this is a shaft that is given to us. There is one bearing here and another one at this point. There are two keyways, one at this point and the other one at this point. And there's a gear here which rotates the shaft, and there's a blade or fan at the end of the shaft. The material of the shaft is steel, and the surface finish is cold drawn. Indra's strength was found in chapter 6, and for this question is 55 kpsi, kilopound per inch squared. And notch sensitivity for keyways for either of them is 1, and that's for both bending and shear case. Okay, and this is the stress strain diagram of the shaft. You see that the elastic part and the yield point necking until the fracture. Okay, before I want to answer this question, I'm gonna try to see if I can get more information from this graph here. This point is my fracture point. In brittle material, it's called rupture. And the sigma stress at fracture point is 170. At this point, this is the peak of the graph. And the stress, which is also known as ultimate point. So this point, this stress is called ultimate strength, and that is 240. This 135 represent that point, and that's a yield point. So that's sigma y. We know that the modulus of elasticity, or Young modulus, is the slope of the linear part of a stress strain diagram. So if I want to find the modulus of elasticity, for this case, this is rise over run and this is the rise, and this amount is 135, and the unit is kpsi, so 135, and the run is this guy, which is 0.0002. So I'm gonna find the Young modulus, which is 67530, and the unit is kpsi. Okay, that was the hidden information that was given to us, not directly, indirectly. Okay, let's continue. In the first part, we were asked to draw the free body diagram. I want to just assume that there is no stress concentration sources, there is no changes in the diameter and nothing. I just want to see the beam as this line, for example. Okay. If I look at this beam, I see that there are two bearings. So I'm going to have two reaction forces at the center of each bearing. So if that's my first bearing, I'm going to have one reaction forces acting on this point, and I'm going to call this one FA. I'm going to call this point point A, and this one point B, this point C, and point D. Okay, I'm not exactly sure if we need point D or, but anyways. And for the second bearing, we're gonna have another reaction force which is FC. Okay. At point at point B, this point, there is some information given in the question. There is a radial force and tangential force at pitch diameter of 2.5. Okay, in order to find that information, let's say that, let's look at this analogy. Let's say I'm looking at the cross section of something, of a gear, for example, and there is one force like that, and one force like this acting on the gear of the shaft, or on the shaft. This force is Fr, and this force is Ft, tangential and radial force. Okay. Before I do anything, if I want to analyze that one, I have to move both forces. I have to move everything to the center of the shaft. Okay. Whenever I want to move any forces to any other points, I need to move the points and the corresponding moment. So if I want to put this force to this point, I'm gonna have one force like that, and I'm gonna call this one, for example, F1. So F1, the value of F1 is exactly the same as the value of that radial force, the force that I'm gonna move, and it's gonna have a moment. But because the load line is passing through the points, so the moment, or I can say the moment is fine. So the moment caused by this force is 0. Okay. Now let's say I want to move this force to the center. So if I want to move this force to the center, that will be the force. I'm going to call that one F2. So F2, the value is the same as the tangential force, that's Ft, but this force makes a moment. Okay, and that moment is in this direction, and I'm gonna call that one T2, because that's like a torque. It's twisting the cross section, so I can say T2. Moment and torques, like, they are found in the same way. So T2 is the amount of force that I had times R, the distance between the force and the center, and this R is pitch radius. So if I come back to the question, the amount of radial force is given to us. So Fr is 6 kilopound, tangential force Ft is 8 kilopound force, and the pitch diameter Rp is 2.5 inches. So I can say my F1 is Fr, which is 6 kilopound. So F1 is 6 kilopound force, and F2 is 8 kilopound force, and T2 is 8 times 2.5, which is 20 kilopound times inch. Okay, this is the information that the question told us. If I come back to this free body diagram here, I said that I have a force like this, and I call that one Fa, the reaction force at the bearing. I have another reaction force at the second bearing. This one, I call that one F of C. And I said I have an external force here at point B. Okay. the amount of external force acting at this point, Fb, is the resultant of F1 and F2. So, for example, if this is my F1, and this is my F2, that Fb is the resultant force, so that is my Fb. Okay, so Fb can be found from F1 squared plus F2 squared, so that will be 10. So Fb is 10 kilopound force. Okay, so when we want to write free body diagrams, we need to show the forces and the distances. Okay, so the distances between the forces and between the force and the end of the beams are important for us. The first distance is this one. Between this force and the end of the beam, this distance is 1/4 of the inch. Between FA and FB, the distance is 9. Between FA and FC, distance is 11. And between FC and the end of the beam is 6. So this distance here was 1/4 of the inch, 1/4. From here to here, this distance was 9. From FA to FC was 11. And from FC to the end of the beam was 6. Okay, so this is the solution for the first part of the question, for the part A. In part A, we are asked to draw a free body diagram. Okay, so that's a free body diagram. I showed the forces and I showed the distances. Okay, in part B, we are asked to find the amount of these forces and torsion and bending, if whatever we have in the question. Okay, first I'm going to start from finding the amount of forces. In order to find the reaction forces, I need to write the equilibrium equations in y direction and moment equation around any arbitrary point, which I'm going to choose point A for this question. So I have two upwards forces, FA and FC, which I don't know how much they are, equals to the downward force, which is FB, and the amount is 10. And for moment, I have FB acting at a distance of 9. That's equals to FC acting at a distance of 11. Or you can write them in any other orders that you want. As long as you keep the signs properly, it doesn't matter. From the second equation, we know that FB is 10, so I just substitute that one with 10. So I can find FC here. FC will be 90/11. And if I substitute that one in the first equation, I can find FB. So FB will be 20/11, if I didn't make a mistake. Okay, so these are the forces, and both are in kilopound. Okay. So that's a force. About the torsion part, we found that the torsion acting on the beam is T2, what we call it T2, and the amount of that is 20 kilopounds times inch. So T is 20 kilopounds times inch. If I come to the question, usually torsion comes to a system at one keyway and goes out from the other one. So in this question, that torque applies at point B, and it's gonna go out. It's gonna going out of the system at point D. So we don't have any torsion before point B and after point D. So I'm gonna note that one here. I'm gonna say this torque. There's a steady torque from point B to point D. Okay. So I found the reaction forces, I found the torsion. Okay, let's talk about the bending. If I want to find bending, I'm gonna use singularity function to find bending moment equation. So for bending, I'm gonna use singularity function. And if you have any questions about this function, there is another video on my channel that you can check that out. So in this case, if I want to use singularity function, I'm going to put my origin here at this end. So that will be my x-axis and that will be my y-axis. And I'm going to do cut at this point, and I'm going to consider this part. So I'm going to have, I can say the moment is FA, is acting upwards, so that's positive. The distance is x minus a quarter, the power is 1, minus external force, which we call that FB. FB, the distance is x minus 9.25, the power is 1, that's minus because acting downwards, and FC, x minus the distance is 11.25, power of 1. Okay, and I'm going to substitute the amount of forces here. So F1 and FC, F1, FA was, how much was FA? Okay, why did I say FB here? That's FA, sorry. FA is 20 over 11, so that's 20 over 11, and FC was 90 over 11, 90 over 11, and FB was 10. Okay. So I found the moment equation. What I can do here, which I'm not asked to, but I can do, is I can write the moment equation as a piecewise function. I can write this equation when x is between 0 and 2.20, a quarter, when x is between a quarter and the second one is 9.25, when x is between 9.25 and 11.25, this point. When I want to break down a moment into some regions, I'm looking at the inside of the brackets and I break down to those numbers, and the length of the total length of the shaft is, this is 6 plus 11 is 17, 17, 25. Okay, and 17, 25. Okay, and for each region I'm gonna find I'm gonna write the moment equation. For the first region, I'm gonna pick a number between 0 and a quarter. If I pick any number in this region, if I put that here, the inside of this bracket will be negative, And because of the properties of the singularity function, the whole terms will be 0. The same for this one and for this one. So at this point, this is 0. The moment is 0. Okay, let me just want to organize this one a little bit. Okay, that's better. In the first region, if I pick any number between 0 and a quarter, if I put in all these brackets, they all will be negative and they all will be 0. So for the first region, moment is 0. For the second region, if I pick a number between these two, like if x is equals to 1, if I put that one here, 1 minus something, 1 minus 11, 25 is minus something, 1 minus 9 stuff is minus something, so that is 0, this is 0, and this part will be positive. So this bracket will be changed to parentheses. So the moment will be 20 over 11 x minus 25, and the power is 1. The third region, if I pick a number here, like if I pick 10, if I put in this function, these two will be positive and this one will be negative. So this will be gone and I just have these two terms. So the moment will be 20 over 11 x minus. So the brackets will be changed to parentheses. Minus 10. And finally, if I pick any number here, all those terms will be positive and all the brackets will be changed to parentheses. Okay. Now at this point, I want to draw moment diagram and torsion diagram for this beam. I'm going to start from the torsion because that's easier. The torsion, we said that that's steady and it comes from one keyway and goes out from the other one. So we have a steady torsion from this point to that point. So torsion will be 0 from here to the first keyway, and we're going to have some steady torsion from the first keyway to the second keyway, like this, and then again we're going to have 0 torsion to the end of the beam after the second keyway. So we just have some torsion between this point and this point here. Okay, and if we want to know the amount of that one, we can just come back to the part B here, and when we talk about the torsion, so the torsion was just 20 kilopounds times inch. So the unit is kilopound times inch, so this number here is 20. Okay. For the moment, if I want to draw a moment diagram, I can look at this piecewise equation. So for the first part, for the first region, the moment is 0. So for the first region, from here to here, the moment is 0. For the second region, the moment, that's a line equation. When we want to draw a line equation, we need 2 points. The best points that we can apply into this equation is the first and end point of the region. I'm going to apply the first point of the region to the second line of equation. So moment, when x is equals to 25, I'm going to say this is m2, because that's the second line. That's equals to 20 over 11, and that is x is 25 minus 25, so that will be 0. So that's my first point, and for the second point, m2 x, so that's for this point. I'm gonna apply this point when x is equal to 9.25. That will be 20 over 11, 9.25 minus 25. So that will be 9. 9 times 20 will be 180 over 11. And the numerical value will be 16.36 kilo pound times inch. Okay, so I found 2 points, and the first point was 0. This is the first point, and the second point was this point, and the amount of that was 1636. So this is 1636, and because that was a line equation, so I just needed 2 points to be able to draw a line. So that's the line. Okay, I'm gonna do the same thing for the third region. I'm gonna find the amount of, because again the highest order that we can see here is 1, so that's a line equation. So m3 so m3 when x is equals to 925 and x is equals to 925, the moment will be, I'm going to apply 925 here, and this part will be 0, and this will be 925 minus 25 will be 9 times 20, 180 divided by 11, so it's going to be the same number, 16.36 kilopounds times inch. And m3 when x is equals to the last point of the beam of the region, which is 1125, minus 25 will be 11. That 11 with this 11 will be cancelled out, so it will be 20 from the first part. 1125 minus 925 will be 2, so 2 times 10 is minus 20. So that will be minus 20, and 20 minus will be 0. Okay, so the first point for the third region is exactly the same point, and the second point for the third region is 0. So I can draw a straight line between these 2 points. And I can do the same thing for the fourth and fifth region, and I'm gonna get 0. Okay, so that's the behavior of moment. And this is what I was asked in part B. In part B, I was asked to find reaction forces, this part, torsion, this part, and moment. But I wanted to do more, so I wrote the moment in a piecewise function, and then I draw moment and I draw torsion diagram, which I wasn't asked, but I did that. So I'm gonna say this is part B. Okay. In part C, we are asked to find a diameter based on Gerber criterion. So this is This is part C. Okay. In order to do this, I need to focus on a point that safety factor is given. If I come back to the question says that the safety factor in the left keyway at this point is 1.5. So I'm going to focus at this point. I'm going to focus at point B. I'm going to say at keyway B. Okay, so if I come back to my moment diagram, this is keyway B. This point. That's my point B. Okay. The amount of moment at this point is 16.36 and the amount of torsion is 20. So I'm going to rewrite the information for that point. So moment at this point is, how much was that? 1636? Is 1636 and torque is 20, and both of them are kilopounds time inch. This is kilopounds time inch. Okay. Now I need to find two important factors for each of them. I don't want to go in details how I can find them because I discussed about them in the previous videos. For the moment, at that point, let's start with the torque. Maybe torque, that's easier. Torque is steady at point B for the whole time. So if that's torque time behavior, torque is steady at all time, and that equals to 20. So in this system, the amplitude of the torque is 0 because there is no fluctuation. So the amplitude is 0. And the mid-range torque is the offset from time axis, which is the same as the value of the torque. So that's 20. So that's the important information that I can get from this graph. Okay. For the moment, story is a little different. As we discussed in the previous lectures, when the shaft is rotating and there is some amount of moment acting on the shaft, this moment makes a completely reverse scenario on the shaft. That means that at point, we are just analyzing point B, one point of the shaft. At point B, at this time, the moment is in maximum value, which is 16.36. But when the shaft is rotating, at this point, at point B, the amount of moment will decrease, and it comes to 0. And again, when we rotate, it goes to some negative value. And that negative one is exactly the same. And then again, it's going to increase, and then go to 0, and then go to maximum, and then come back, and continues like this. And this behavior is called completely reversed scenario. Completely reversed. Okay, so in completely reversed scenario, this is the amplitude. So MA is 16.36 and there is no offset, so M mid-range moment is 0. Okay, so we can get these two informations from these two lines. For each line we need to know amplitude and offset. Okay, There are two other important things that we need to find, and those are the fatigue stress concentration factors. If I want to find KF, fatigue stress concentration, that's a capital K, KF is 1 plus Q KT minus 1. And this Q is notch sensitivity, and this KT is its theoretical stress concentration. Okay, and these two can be found from tables. This is from Q can be found from two tables, and KT can be found from Appendix 15 and 16. In this case, this Q is given to us, and it says that that Q can be assumed 1, because ultimate strength here is 240. It's 240, and if I come to the Q graph, I see that 240 is somewhere here. So having Q, if we consider Q is 1, it's not an unrealistic assumption. So that's perfectly that looks nice. That looks fine to us. Okay, so this Q is 1 in this question, and this KT should found from table from Appendix 15 or 16. So I have to go to the Appendix 15 and 16, and I have to find this case when there is a keyway. That's point B, yes? This is point B, okay? But when I go to those appendix, I see that I cannot find something like this in the appendix. In those cases, we have to use we can use table 7.1 in order to find theoretical stress concentration. So I can come to this table, and the question, it says that we have end mill key seat. So this is the case that we are studying. So I can read these two or any numbers that are here. So in this case, I don't have any number for axial. I don't have any axial force. So I don't need that one. But this is KT, and this one is KTS for the shear and just for the normal or for bending. Okay, there is something here that I want to mention before I want to continue. Whatever you see here, R over D is 2% for this part. That's an assumption. It says that in this case, if you are in this line, you can assume that R over D is 2%, and usually D is given to us. So from this equation, we can find R, and once we get R, we can come to this graph, because this is sorted by R. So based on R and the ultimate strength that we have, I can read Q. But in this question, it made it easier for us, and it said that Q is 1. Plus, we don't know what D is. We are asked to find D. Okay, so KT here is 2.14 and KTS is 3. So I'm gonna find KF based on this equation here. Which is 1 plus Q KT minus 1, because this is 1 So that will be just KT, that will be 2.14, and I'm gonna find KFS, which is 1 plus QS KTS minus 1, which in this case, because that's 1, so these two 1 will be cancelled out, and I'm gonna have just 3. Okay, now I can go to the criterion that I'm asked, and I can find whatever I'm asked to. Okay, here we're gonna use Gerber criterion, and we're gonna consider distortion energy failure in that. Okay, in the previous page we found that TA is 0, so this guy will be 0, and MM was 0. Okay, so because TA, let me write it here, TA was 0 and MM was 0, TM was 20 and MA was 1636. This is the information that we got in the previous page. I just put them here. Okay, so this A will be 2 KF MA. So will be 2, and we found KF in the previous page here, that is 2.14, 2.14, MA is 1636, so that will be 72. Okay, for the B, for this guy, that will be square root of 3 KFS TM, which will be KFS from the previous page was 3 and TM was 20, so that will be 103.92, and these are the unit of this one is kilopound times inch, so that's kilopounds times inch. Okay, in this question I'm asked to find the diameter, so I don't need to use this equation, and I just need to use the second equation to find the diameter, and n is given to us, which is 1.5. So the safety factor is given to us, and that's 1.5. So I'm looking at this one, and I'm seeing that I have N, I have A, this one, I have B, SE, SUT, SE, they are all given to me. So I can find the diameter. I'm gonna find this term first. 8N times A, so that will be 8. N is 1.5. A is 70.2, okay. The denominator is pi times 55, so this number will be 486. Okay, and now I'm gonna find this guy here. That is 2 times A, sorry, times B, 103.92 times SE, which is 55. that's A, and SUT is 240. Okay, before I want to continue, I'm gonna double check the units. For this one, the unit of this A is kilopounds times inch. And the unit of this SE here is, if I come back to the first slide, this is the information that I'm talking about. This is SE 55, SUT 240. They are based on kpsi. So I have 110 to the power of 3 here and 110 to the power of 3 here. So they can be cancelled out, and like I can have just this one here. For this one, in the B, I have 110 to the power of 3 inside of that here. That's a kilopound. And this SE here, that's again is in kilo psi. I'm going to have one SUT here. So if I had any other units, I could put those. I could use use an appropriate conversion factors in order to get the same units. I just want to double check if everything is okay, and this is what you need to do in the future if you are confused about the units. Okay. So once I get these two, I can come to the equation. The equation says 3 cube is equals to 486, 1 plus square root of 1 plus 8 power of 2, and this is that. So it will be 486, and that integral, the result will be 1.25, so that will be 1074, and that's d cube. So the diameter will be 2.21 inches. Okay. So let's go to part D. In order to find the deflection equation, there are a couple of ways. The method that I'm going to use here is called double integration method. In this method, I need to know the Young modulus of the beam, which I found in the first step, and that was 675,000 kpsi. I need to know the second moment of inertia. Here we have a shaft with circular cross section, and that's p d to the power of 464. And because in part D it said that let's assume that the diameter of the shaft is constant and is 1.5 for the whole shaft, just substitute that one here. So that will be pi 1.5 to the power of 4 over 64, and the answer will be 248. The unit is inch to the power of 4. And I need to find the rigidity of the system. Rigidity is E times I. In this case, that will be 167 times 0.74, 10 to the power of 3, and the unit is kpsi, inch to the power of 4, or because that is kilopounds per inch squared, I can say that is kilopound inch to the power of 2 inches squared. Okay, or it doesn't matter like which unit. I mean, it matters, but we just need to be careful to take the right factors. So in the in the double integration method, we need to have m moment equation, and we can find slope based on this formula m over ei dx. So it gives us the slope. So that's slope, and we can find deflection by finding the integral of slope. And that's deflection. Okay. And for finding moment, I'm going to use singularity function, which I've already used that in the first part of this question. So moment for this problem is 20 over 11 x minus a quarter to the power of 1 minus 10 x minus 9 and a quarter power of 1 plus 90 over 11 x minus 11 quarter to the power of 1. Okay, so that's my moment equation. What I need to do now, I need to find the slope based on this equation. So the slope will be the integral of m ei dx. But because ei is constant in this question, it can come out from the integral, so that will be integral of ei m dx. So I can find ei times theta, that will be integral of m dx. Okay, I'm gonna find this term. So ei times theta will be the integral of m, integral of this function here, that will be 10 over 11 x minus a quarter to the power of 2 minus 5 x minus 9 and a quarter to the power of 2 plus 90 over 22 x minus 11 and a quarter to the power of 2. And because we are doing infinite integral here, we should consider a constant like c1. Okay, so that's my, if I want to find theta here, I can just put this ei as a denominator for this big term. So I'm going to find deflection, or deflection, which will be 1 over ei, the integral of this part, which will be 10 over 33 x minus 1 over 4, 2 minus 5 over 3 x minus 9 4, 2, oh sorry, this is 3, this is 3 plus 15 over 11 x minus 11 4 to the power of 3. The integral of this one will be c1 times x. Because we are doing an infinite integral, we're going to have a constant like c2. Okay, so this is the equation for y. But this equation here, we have two unknown terms, c1 and c2. These two unknowns can be found from the boundary conditions. The boundary conditions for this question is the deflection at this point and this point will be 0. Because, for example, like after loading, maybe this beam will be something like this. I'm just saying. I know I'm exaggerating, but at these 2 points, because we have bearing, so the deflection will be 0. The position of the first point is 1 point is a quarter after the origin, and the position of the second point is 11 and a quarter after the origin. So at x equals to a quarter, we know that the deflection should be 0. So we're gonna put we're gonna put quarter in this equation here. This term will be 0, this term will be 0, this term will be 0, because the inside of the bracket is negative, so these two will be 0. And I'm gonna have 0, that's y, equals 1 over EI. And from the right hand side, I have C1 times x, so that will be C1 over 4 plus C2. And at x equals to 11 quarter here, y will be 0. So 0 equals to 1 EI. So if I put 11 and quarter here, that will be 0. But these two will be positive, so I have to find the value. So 11 and a quarter minus a quarter will be 11. 11 to the power of 3. So that will be 10 over 13. That's 11 to the power of 3. Minus here 11 and a quarter minus 9 and a quarter will be 2 to the power of 3 is 8. 8 times 5, 40, 40 divided by 3. So minus 40 divided by 3. And plus C1, that's 45 for C1 plus C2. Okay. So by solving these two equations, I can find C1 and C2. So C1 in this question will be minus 390 over 11, and C2 will be 195 over 22. And the equation for y, if I can rewrite that, but that will be 1 over rigidity, this guy. And this is what we found here. Yes. And we need to substitute C1 and C2 in this equation. And that's a deflection equation. And finally, the bonus part of this question is asked to check for the yielding. Whenever you want to check for the yielding, these are the questions 15 and 16 from chapter 7 of Shigley's book that I brought it here. We need to find the maximum von Mises stress, this one. And this one, the equation for that is this. So if you want to find for the yielding, we know Sy from the question. In this question, Sy is given to us, and Sy is 135 kpsi. And if I want to find sigma max prime, I can just find this guy here, and I know that in this question m mid-range moment is 0 and amplitude of the torque is 0, so these are 0. So the first term will be, so I'm gonna say sigma max prime is square root of a very big thing, and here I have 32 times 2.14 times 16.32. I just applied whatever we found in the previous step. Pi times 221. And we need to be careful about the units. Okay, so the whole part, this one, is to the power of 2 plus 3 times the 16, 3, 20. This is the power of 2. And the denominator is pi times 2.20 to the power of 3. So I can simplify that one. That will be 32.96 to the power of 2 plus 3, 28.31 to the power of 2, and the square root of this. And finally the answer will be 59.08 kpsi. And I can come here and find ny. So ny will be sy 135 over 59.08, and they must have the same unit, and the answer is 2.28. And this is how we checked for the yielding. But if you wanted to have a quick check, instead of finding this big fraction here, you could just assume that sigma max prime equals to sigma a prime plus sigma m prime, and in that case you would find another n, but because that's more conservative than this one, so like we are okay, so we shouldn't be worried. That's for just quick check. So I'm gonna say for quick check you could also use this method here. Okay, thank you.